Alright, so the video gave us an introduction to the idea of identities, but let's talk a little bit more about what an identity actually is. The video that you just watched said that an identity shows equivalence, but what you need to realize is that it's not equivalent values as much as it is equivalent statements. What that means is that for any value of the variable, the statement is always going to be true. So when you have an identity, you have a statement that no matter what you put in for the variable, your statement is always going to be true. Here's an example. What's the difference between having a statement like 3x plus 4 equals 19 or having a statement like 2 times x minus 4 equals 2x minus 8? Well, the difference is what values make the statement true. In this statement, can I use any value for x and have this statement always be true? Well, I hope you realize that answer is no. The only value of x that makes this statement true is when x equals 5. So this is a statement that has an equivalent sign in it that's saying I want this side, my 3x plus 4, to be equal to the 19, and I need to find the value of x that makes that happen, but there's only one value of x that happens for, or there's a limited number of solutions that is going to make this equation true. But now let's go over to this one. What happens if I put any and all values in for x in this statement? Can you find values of x that make the statement true? How many values of x can you find that make the statement true? Maybe the better question is, can you find any values of x that make this statement false? And the answer is no. Everything works in this statement. And I think you can probably see why. We know that if I distribute the 2, I get 2x minus 8. So I have one form of the statement here. I have another equivalent form of the statement, of the expression here. And no matter what I put in for x, these two sides are always going to be equal to each other. So this is always going to be true. That's what makes this an identity. And this is an equation to solve. Okay? All right, so the video introduced you to 3 identities, 3 statements already, where the one side is equivalent to the other side for any value of the theta, any value of the angle. There are 2 more that we need to add to that list and add to your notes. The first one is called the co-function identity. And the co-function identity makes the connection between the functions that are complements of each other. So for example, sine and cosine are complements of each other. And so one of the co-function identities says, let me just cover this up so I don't smear it, says that if I take the sine of pi over 2 minus theta, that is equivalent to just taking the cosine of theta. And so what this allows us to do is it allows us to change back and forth between a sine and a cosine. If I have sine of this type of an expression, I can simplify it by simply changing it to cosine of just whatever theta is. And vice versa. If I have the cosine of pi over 2 minus theta, then that's simply equal to the same thing as the sine of theta. And again, this works for any value of theta. This is always going to be a true statement. The other complementary trig functions that we have are the tangent and cotangent. And so if I take the tangent of pi over 2 minus theta, that is equivalent to the cotangent of theta. Okay, so that's another set of identities that we need to know. And then our final set is what's called the even-odd identity. And in the even-odd identity, it allows us to deal with negatives more efficiently. And it's based on the type of function sine and cosine and tangent are. So when you take the sine of a negative angle, well, if you think about that, we know positive angles are supposed to rotate clockwise. So if I have something with this much of an angle, I'm talking about right there. And we know the sine is going to be our vertical distance here. Well, if I go that same amount, but I go negative, meaning that I go clockwise, then my distance here should be the same, but the distance is below the x-axis. So this is actually a negative value now. So it's going to be the same sine as what I got up here, but negative. And so that's what my identity says. Taking the sine of a negative theta is the same as having negative sine of theta. Okay, so this is telling us that if we have a negative on the inside of the sine function, we can take it to the outside and it will mean the same thing. Now, what about with cosine? What happens if I take cosine of negative theta? Well, if we go through the same logic, going up a positive angle means that when I draw my triangle, this is the cosine. Now if I do the same as a negative angle and draw my triangle, it is still the same exact value for cosine. It didn't go negative, it's still the same positive cosine value that we had when it was a positive theta. So taking the cosine of negative theta is just the same as cosine theta. This is what's called an odd function. The sine is an odd function because of the way this works. This is what's called a even function because of the way the cosine works. And that's where the name for our identity comes from, the even-odd identity. Now, tangent, actually, since it works like sine, let's put it over here. Taking the tangent of a negative theta works just like sine does. It's going to be equal to negative tangent of theta. So sine and tangent will each take the negative out in front. Cosine, you can just get rid of the negative altogether because it's not going to make a difference. All right, so how do we use these identities now? Well, there's a couple of ways you can use them. One of the ways is to actually find answers, find values. Things like this. You've seen this kind of problem before, but identities give us a new approach to this problem. So let's say I tell you that the sine of theta is equal to 3/5. And I also tell you that I know that theta is some angle measurement between pi over 2 and pi. Okay? So that's the information we're being given. What we want to find are the 5 other trig functions. Okay, now as I said, we saw this kind of a problem in the last chapter, but we can also consider this kind of problem using identities. We know from the Pythagorean identity that sine squared of theta plus cosine squared of theta has to equal 1. Well, I now know what my sine of theta is equal to. So I'm going to put that value into this equation in place of sine. So that means I'm going to have 3/5 being squared plus the cosine squared, which has to equal 1. Okay? Well, 3/5 squared is going to give us 9/25. And since I'm going to want to subtract the 9/25 from the 1, I might want to think about my 1 in terms of 25ths. So that when I subtract, the cosine squared of theta is going to equal 16/25. And now when I square root both sides, cosine of theta will have to equal plus or minus 4/5. Okay, don't forget about that plus or minus because we're taking the square root as part of solving an equation. So, which one should it be? Should it be the plus or should it be the minus? Well, that's where this extra piece of information comes in. The fact that they were telling us that our theta is supposed to be between pi over 2 and pi is their way of saying that theta has to be in quadrant 2. And in quadrant 2, cosine is negative. So we know we should use the negative cosine value for that. Okay, so now we know that the sine of theta is the 3/5 that we were given. We now know the cosine of theta is a negative 4/5. How do we find tangent? Well, for tangent, we can now use the quotient identity, which says that tangent is equal to the sine of theta over the cosine of theta. Sine of theta was 3/5. Cosine of theta was negative 4/5. That means my tangent of theta is going to be a negative 3/4. Okay? And then for my cosecant, my secant, and my cotangent, I just use the reciprocal identities, which, as the video said, you should already be familiar with. Cosecant will be 5/3. Secant will be -5/4. Cotangent is going to be -4/3. And there's the answer to our question. So that's one way that you can use these identities, is to help you find other trig values in a problem like this. But probably the more common way to use trig identities is in simplifying expressions, simplifying equations, being able to rewrite expressions in another way that is more helpful or more useful or is a better fit for what's going on. So for example, let's say I ask you to simplify the expression secant theta tangent squared theta plus secant theta. Now, on first glance, that might look a little bit complicated, but it's not as complicated as you want to think it is. What we need to look for are two things. We want to look for the algebra that we can do to help us simplify, and we want to look for the identities that we can use to substitute. So the algebra allows us to rewrite things in certain ways based on algebraic rules. The identities allow us to rewrite things in certain ways based on substitution, being able to take a piece of the expression and substitute it with something else that is a better fit. So let's go back to our expression. The first thing we need to realize is if we have these two trig expressions side by side and there's nothing in between them, then that indicates these are being multiplied together. So we're saying it's secant theta times tangent squared theta and then plus another secant theta. Okay? So you start looking, you start thinking about what kind of algebra can I do, what kind of identities might fit. And one thing you might notice is that we have a common factor. The term to the left of the plus sign and the term to the right of the plus sign both contain secant theta. So we know that if we have a common factor, we should be able to factor. So let's try that. Now, one thing you have to be willing to do when you're working with identities is to try things and to retry things. One of the difficulties sometimes with using identities is that there is not one particular way to go about these problems. There are lots of different possibilities, lots of different ways that are going to work, and the only way you get good at it is through lots of practice. And so you have to be willing to try something to see if that helped. If it didn't, to go back and try something else. If it seems like it did, then to continue on to your next step. But you cannot be afraid to try something, and if it doesn't seem like it's working or it doesn't seem like it's helpful, to go back and try something else. So if I factor out a secant of theta, that leaves me with tangent squared theta plus 1. So the question is, was that helpful? Was it helpful to me to factor out secant theta? Well, one of the things I can do is go to my list of identities and take a look to see, is there anything in my list that looks like I could use it for the next step? Okay, so let's try to put these side by side. So do you see anything on your list of identities here that's going to be helpful for your next step here? And I believe the answer is yes. Right here we have a phrase or an expression that says tangent squared of theta plus 1. Based on our identities, we can see that tangent squared theta plus 1 is equivalent to secant squared theta. So I can replace the tangent squared theta plus 1 with a secant squared theta. The identities tell me that they are equivalent all the time, so I can replace the one expression with the other expression. And because I also have secant of theta still out here, it seems to be a better fit. Because now I can take a secant squared times another secant to get a much simpler form of this expression, which is simply secant cubed of theta. So that's what we mean by simplifying, taking something that's a little bit complicated and a little bit scary at first and working through it with both algebraic and identity methods to get it down to something much simpler. Okay? And even when your initial expression seems extremely complicated, you have to just think of it like a puzzle. Think of it piece by piece. Think about what's going to fit best and try to get yourself into a situation where you can factor, where you can cancel, where you can replace things with simpler things to get things to work out. So let's try one more example. Let's try something a little more complex this time. So let's say we want to simplify the secant of x times the sine of x plus the cosine of pi over 2 minus x, all of that over 1 plus the secant of x. What do you think? Are you frightened? Are you thinking, oh my goodness, how ugly is that expression to try to work with? It's okay. As an initial response, it's okay to think that things are ugly, to think that things are complicated, but don't stay there. Once you've gotten over the initial shock, start working it out piece by piece. So where would we start? Do you see anything algebraic that you think would help? Do you see anything in your identities that you think would help? What you cannot do is cancel out the secants. Remember that if you're going to cancel something from a numerator and a denominator, it has to be a factor. The fact that I'm taking 1 plus secant does not make secant x a factor, so it cannot be canceled with anything else. So do not try to cancel secant x, at least not at this point. So what can we do? I don't really see much for algebra, so let's go to our identities again. Do you see any identity that fits any piece of this expression I'm starting with? I think I'm kind of liking this one. The fact that the cosine of pi over 2 minus theta is equivalent to sine theta. That would be much easier to work with in that spot. So let's try that. In place of cosine of pi over 2 minus x, I'm going to replace that with sine of x. Everything else is the same. I haven't touched anything else, so I still have secant x and sine x and a plus and everything over 1 plus secant x. Now, does that seem helpful? I hope you're saying yes, because now I have common factors. In the numerator, in just the numerator, my two terms have a common factor of sine x. So I'm going to take that common factor of sine x, and I'm going to factor that out. And that means I'm going to have left in the parentheses a secant x from my first term plus a 1 from my second term. Because remember, when I factor out, I'm dividing out. So sine x divided by sine x is going to give me 1. Now again, that only affected the numerator, so I still have in my denominator 1 plus secant x. Does that seem helpful? Absolutely, because now look what happens in my numerator and my denominator. I now have a common factor of secant x plus 1. Because it's addition, the order does not matter. So secant x plus 1 in the numerator and 1 plus secant x in the denominator really are equivalent to each other. Secant x plus 1 in the numerator is now a factor of the numerator, and therefore the entire thing can be canceled with the entire matching expression on the bottom. So I'm going to cancel the secant x plus 1 with the 1 plus secant x on the bottom. My blue's not working very well. Let me try green here. Okay, and so what are we left with? Sine x. Doesn't get much simpler than a single trig function. So we took this ugly, complicated, complex expression that we started with, and by going piece by piece, step by step, looking for algebra and identities that will make things keep moving, that would be helpful moves that are going to get us simpler and simpler and simpler, we eventually get down to just sine of x. That's pretty simple. And that's what you're going to be asked to do in your practice. You are given 15 different expressions that you're going to be asked to simplify down to its most simple expression. There is more than one way to get to those answers. So if you're comparing answers and you have something different than someone sitting beside you, it doesn't mean either one of you did anything wrong. Even in terms of what is the simplest answer, there might be more than one possibility. So if you have any questions when you're checking your work with the answers, please get in contact with me and ask me, could this also be a correct answer? And I will get back to you as soon as I can with a yes or a no. Okay, but that's what you're going to be practicing. And yes, there are 15 of them because, as I mentioned at the beginning of this section, the more you practice, the better you're going to get at this. So, keep those identities handy so that you can keep looking at them as you work, and give 7.3 practice a try. If you have any issues, find someone who can help you, find the resources that will help you to figure it out, and I wish you good luck. We'll see you next lesson.